Hello. A couple of days ago, I had a free evening and I created this little particle scene you saw at the beginning of the video. And I decided to create a little tutorial series for it. I won't go into too many details and keep it rather straight to the point, but if you have a good idea of the basic working concepts in Houdini, you should have no problem following along at all. First, I would like to break it down a little bit before we get to the real meat. The whole scene is basically made of two particle systems. The first particle system, obviously, is the big one, those vertical streams going upwards. The second particle system is this little particle system here on the ground. It's basically pretty close in terms of motion in comparison to the big one, but it's much more subtle and it's more like a filling object. So the ground isn't all that naked. And the third element of the scene is the ground plane itself, rendered with a noise and low opacity to fill in all those negative spaces here. And I thought of it acting like an atmosphere, maybe some nebula stuff, something like this. And yeah, that's pretty much it. 3 elements. So let's get started with the basic setups, I guess. To begin with, let's lay down a couple of geonodes. First one will be for our effects elements. So let's name it fx_particles and create a couple of more, name them ren_vertical particles, all direct to duplicate. Let's dive into the fx container. For starters, I will lay down the grid. So the first thing I did was to create an interesting noise on this grid to get a pretty irregular spawn area for the particles. So the first thing we need to do is we need to get some resolution. I will remesh the grid for this purpose. So that should be plenty of resolution to work with. Next thing, we will lay down a point warp. In the point warp, I created a unified noise static and fed the output noise in the color diffuse. After that, I changed the fractal type to standard, reduced the max octaves to 3, I guess, and reduced the overall roughness a little bit. I also reduced the frequency down to something like 0.3. Then I created a vector and fed time into the Y component and hooked this vector up into the noises offset. So we get a nice movement over time. Using a multiply constant, I reduced the time by a factor of 3, so we get a much slower movement. Looking at the output values of the noise, we can see that the range goes from 1 to 0.1, so we can use a fit node to get the full dynamic range of the noise into a normalized space. So if we change the source min to 0.1, and I also like to add a power function right behind it, change the exponent to something like 2, so we get a nice contrasty noise. After the exponential raise, we can use another fit range node and push the contrast to the limit really. Once we're happy with that, we can use a logarithm node and lower the base factor. We can pretty much isolate the outlines of those individual islands. Those bright parts here, they will act as an emission attribute. So wherever the area is bright, particles will be spawned. And the darker it gets, the less and less particles will be spawned. I just wanted to do a little math break and lose a few words about the logarithm function and why I used it in this case. Of course, there are other methods we could have used, for instance, just a simple ramp to isolate those areas. But personally, I like math, and so I decided, yeah, why not? For this example, I would like to create a little pseudo two-dimensional coordinate system by dropping down a line and orientating it towards the positive x-axis like this. I'm increasing the point count to, I don't know, 32. Okay, if I change the view to front, we can imagine this being a two-dimensional coordinate system. Let's append a vector to float and append a float to vector to recombine it. So we hook x into x, and our y position will be x with the logarithm function as the y-axis. So with the base value being basically the Euler number, you can see the logarithm function doesn't return a usable range for us. However, if we lower the base below 1, so what does it mean? A value of 0 will return effectively 0, and a value of 1 will effectively return 0 as well. To make it applicable for our case, I took the screenshot here. If we look at those areas, they're all black, meaning they have a value of 0. And those areas here, they have a value of, I don't know, something like 1. And those areas here in between, they interpolate between 0 and 1. And when you compare it to the function, the values between 1 and 0, like in this area, they will have a certain value other than 0. So we are effectively isolating those fall-off areas. Okay, the noise already looks quite cool, but we can go even more crazy. So we can use another noise, anti-aliased flow noise, to distort our position before we feed it into the unified static noise. If you lower the frequency of the AA flow noise really low and maybe decrease the octaves and set the amplitude before, we can get even more way crazier shapes. And if that's not crazy enough yet, there's another cool thing we can do. We can lay down a transform matrix and put it in between our distorted position and the unified noise. If we now rotate it, you can see we can rotate our position. We can scale our position vectors. Let's lay down turbulent noise. Lay down a fit range node. With this noise, I would like to modulate the scale. Set the destination min to 1 first. Hook this one up into scale. Nothing changes because the scale will be 1 if we reduce the destination min. You can see now certain parts of the noise will be scaled. We can also do the same thing basically with the rotation. So we can use another noise, change the offset, use another fit range, change the output range to something like, I don't know, minus 30 to 30. This is in degrees, by the way. And put this up into rotation. Now we need to adjust our fit range in the end a little bit to get a razor sharp line. Something like this. And this will be the emission area for our vertical particles, so for the first particle system. For the second particle system, we will use the same WOP, so I'll drag it to make a duplicate. Let's dive inside, bypass the logarithm node with a Q, and we will also get our range back. And this one will act as the source area for the ground particles. Now we will duplicate the WOP one more time and change the range again, so we get all the information back, basically. And we will use this noise actually to drive the shader of our ground plane.